Okay, so we have had a look at current, we've had a look at charge. Next on our to-do list is potential difference or voltage. Right, first things first. This seems to be, for whatever reason, the one bit of electricity that people struggle on the most, at least in my experience. My GCSE, my A-level students, they tend to find, charge and current, that makes sense. Current, the guys going around the circuit, carrying everything along, and charge is a thing that they all have, and that's fine. But it's when we get to voltage and potential difference that we tend to get a little bit confused. Now, one of the reasons I think that might be is because we have two words for it, right? Sometimes we call it voltage, and sometimes we call it potential difference. So the very first thing that I want to get across is that these are the same thing, okay? For most, practical purposes. Whenever we reference voltage, we are talking about potential difference, okay? Potential difference is the more formal way of saying it, and we may potentially see why a bit later, not in this video, but in general, these are the same thing. So what is it? Well, if we have a circuit, just here is a bare basic, it's a lamp and a cell, right? Nothing crazy, it's a lamp and a cell powering a lamp. What is the core thing that we need to get that lamp to turn on? If you're thinking current or charge, or maybe you've said potential difference or voltage, yeah, absolutely, we do need those. But on the fundamental level, remove all of the nonsense from electricity. If you asked a 6-year-old, what do we need for that lamp to turn on? Well, the 6-year-old would probably say light and they'd be wrong. But the very core thing is we need energy, right? For anything in the universe to work, we need some energy. That is all we need. Yeah, we have a whole hullabaloo of how to get that energy, and we have the charge and the current and all that nonsense. But at the end of the day, if I want my lamp to turn on, I need to give it some energy. That is what the voltage or the potential difference is akin to. When we talk about voltage and potential difference, we need to think about it as, it's the energy that I'm giving my lamp for it to turn on. So, here's my analogy that we come up with. Now, I recorded the current video about 8 months ago, but I'm going to try and use a very similar analogy to it. Can't quite remember what the analogy was. I have a couple that I kind of roll with, but I'm going to use my analogy of here are all my electrons. Of course, it might not be electrons. It could be any kind of ion. But here are my electrons coming out of my cell. And they are going around my circuit. They're going towards my lamp. The amount of electrons that I have is my current. Yes? If I put a little marker here and I counted how many are passing by that every single second, that is my current. How many of them do I have flowing? That is my current. But just having them go all the way around to my lamp isn't going to do anything. Just flowing round and flowing through my lamp aren't going to do anything. They have got to transfer energy to my lamp. Each of these electrons has got to have some energy in it in order to do their job. So, we're going to find out where they get this energy from a little bit later, but for now, let's just be comfortable with the fact that they are flowing around, that's my current, and they are each carrying energy. When my electrons reach my lamp, they are going to have to transfer some of the energy that they have collected to my lamp. Yes, lamp needs energy to turn on. Energy can't be created or destroyed. It's got to get it from somewhere. It gets it from my electrons. So my electrons turn up at my lamp and deposit some energy in that lamp. They deposit the energy and then they, continue on their way all the way back into the battery. Yeah, this is our analogy of how things work. It isn't exact, it isn't, specifically, physically, scientifically true, but it's a good enough analogy of what's happening. It will help us to do the calculations and conceptually understand it. So, my electrons have gotten some energy, they have taken it to my lamp and they have deposited that energy. Now, clearly, depending on what my lamp is, right? If it was a little torch you might put on a key ring versus, a floodlight that you might have on a football pitch, they're obviously going to need two different types of energy. This is where voltage comes in. Voltage, specifically, is the energy or the work done per unit charge. So each of my unit charges is doing work, is giving energy to the components in the circuit. Each component will need a different amount of work done. So, how do we measure that? Well, if I wanted to know how much energy my lamp is using, well, the simplest thing to do would be to have a look at my electrons about here, just before they enter my lamp, and check how much energy do they have. Yeah. Let's say, again, we don't usually use joules in electricity, but let's just say they had 100 joules before they go in. And then when they come out, they had 20 joules. Well, it doesn't take someone with a maths degree to work out that my lamp has sucked out 80 joules. Right, so my lamp requires 80 joules of energy. And this is exactly what we do. We check the electrons or the charge carriers before, we check them after, and we find the difference in the energy. This is why my voltmeter sits around a component like this. I'm checking the energy there, I'm checking the energy here, and my voltmeter is finding the difference between them. It is finding the difference in my potential. This is where we get potential difference from. Okay, so this is what a voltmeter looks like here. We are measuring the energy difference and we are saying that that is the voltage. Specifically, it is the work done by each of these electrons, each of these charge carriers. So, where does it get this energy from? Well, there's only one other thing in this cell. And that's the cell in this circuit, and that's the cell. The only other thing is the cell. And evidently this is where they get their energy from. A cell, a battery, some kind of power source. Our electrons are, for all intents and purposes, floating around my battery or my cell. My cell gives them some energy so they can go on their merry way. Then they give the energy to the component. They go back around into my cell, pick up some more energy, go again. And we get this fluid motion. Yeah. So, we have got two definitions that are very, very key. The first one is voltage. This is what we have measured on my component here. And I'm going to write this, I'll use my sleeve. I'm going to write this over here. So, I might just put that equation up here just in case we need it later. V is equal to W over Q, work done per charge carrier, or unit charge. And I'm going to say that voltage, which is this guy here that I've measured, is the work done by a charge carrier. Yeah? It is the energy given by a charge carrier to a component. That is my work done. So, I must have the other way round. I must have something doing work on the charge carrier, which is the energy I get from the battery. And for that, we have a very special word, which is EMF, electromotive force. This is the work done on a charge carrier. I do notice when watching my videos back that there tends to be quite a slant at the other end of the board, so I apologise for that, but I think that's readable. So, it's all to do with energy. My electron is in my battery. The battery has a certain EMF around it. Let's say it's a 12-volt battery. A 12-volt battery, for now, means that it is doing 12 units of work done on each charge carrier. That is my EMF. Work done on the charge carrier. They're given that work done, they carry it all the way around, carry it into the lamp, and this lamp has 5 volts, requires 5 volts. So, each of my charge carriers is doing 5 volts of work. That's how we can kind of think about it. Now, hopefully that wasn't overtly confusing, okay? But all we need to remember is it's all to do with energy. Now, a couple of caveats. Voltage is not a unit of energy, okay? We measure voltage in volts, okay? But it is not a unit of energy. It is joules per coulomb. Appreciate there's 2 V's, might get slightly confusing, especially if you try and throw in velocity in there as well. Be very, very careful with all of that. But a volt is a joule per coulomb. How much energy is each coulomb of charge doing in order to power my object or component? Okay, we're going to leave the basic definition of voltage here. I think in the next video, we're going to have a look at how to calculate it in a circuit. So things like Kirchhoff's second law, etc. But for now, we're going to leave it here and we're going to remember these 2 very important things.